So our next speaker is Lin Tian from UC Merced, and she's going to talk about detector readout of analog quantum simulators.
So, good morning. First, I would like to thank Irfan for inviting me to this very exciting conference, and also congratulations for the inauguration of the new Center on Quantum Coherent Sense. So what I'm going to talk about today is, so basically the question I want to answer is highlighted here. So whether a detector readout can accurately tell us the quantum many-body correlations in quantum simulators. So initially, you might think this is a very bizarre question because in traditional condensed matter systems, you just measure your system. You never has a question of whether my measurement going to give me the accurate characterization of the many-body correlations. So this is basically related to work we recently done. One work we just put in the archive last December. So this is in collaboration with Iris Schwank, who actually just learned how to pronounce her name yesterday, and Michelle Matler. Both of those guys work in Gert Schön's group in Karlsruhe Institute of Technology. Another work I'm going to talk about is with Liang Huidu, who is a postdoc in my group, and Jianqiang Yu from CSRC in Beijing. And before I go on with the question, I'm going to first give you a brief overview of analog quantum simulation and several previous work we've done on the implementation of quantum simulators with superconducting system. So quantum simulation was first discussed in 1982 in one of the papers of Richard Feynman. So the idea is basically use one quantum system to emulate the behavior, dynamics, or maybe ground state properties of another quantum system that is hard to study classically. So there has been basically discussions on building engineered quantum systems to mimic novel many-body systems to solve the question that can hardly be solved with traditional techniques. There also has been discussions on digital and analog quantum simulators, and even hybrid quantum simulators use both digital ideas of basic performing quantum logic gates and also analog quantum simulator ideas of constructing many-body Hamiltonians. So there has been discussions on what would be the central questions in doing analog quantum simulation. And so there are a list of questions I think analog quantum simulator need to be fulfilled to basically to have a successful analog quantum simulation. So one is, of course, you need to be able to successfully prepare the many-body Hamiltonian for the model that you are interested in. And also, once you have such Hamiltonian, you need to be able to change your parameters in the parameter regions of interest. For example, if you want to observe quantum phase transition in a simulated Fermi-Hubbard model, you need to be able to change your parameters between the regions of different many-body phases. And there's also the question of prepare the system in the proper, for example, ground state or stationary state. And then there's a question of the detection of the simulation of the correlations in the simulated model, which is directly related to what I'm going to talk about today. And also there's also the effect of noise and also control errors in quantum simulators. So many of those criteria is less strict than the requirement for building a scalable, fault-tolerant quantum computer, but there are also non-trivial conditions. So with superconducting devices in the past 30 or 40 years or so, there has been enormous progress starting from basically a basic research in studying a microscopic quantum tunneling, like what we heard in the past couple of days. And also until now, you really have the aim of building a scalable quantum computer, large-scale quantum computer. So one basic type of device is, of course, a qubit. So this is can be used to emulate quantum spin systems, and also in 1D, you can use this to simulate fermions by performing the Jordan-Wigner transformation. And there's also superconducting resonators. which can be seen as basically a bosonic mode that can emulate, for example, phonons. And both type of devices can be used as probe of quantum simulators. So by coupling those devices together, you can build many different designs of quantum systems because of the rich connectivity and controllability of the superconducting devices. We have also observed improved decoherence times that basically improved by orders of magnitude in the past 10 or 20 years or so. And so there has been a number of experimental work towards realizing quantum simulation in the past few years. You have heard about the experimental results from Irfan's group in basically on Monday. And also I think we're going to have a couple of talks along this direction in today's sessions. And so one model we studied in my group is something we call the multi-connected Jens-Cummings model. So here you basically have, think about in the simplest scenario in a 1D system. So you have basically alternatively connected qubit and resonators. For example, if you look at this, this diagram, so you have each qubit connected to the resonator on the left-hand side and also on the right-hand side. So with this coupling Hamiltonian, we have shown that when you have integer filling in the system, you put basically excitations in the system, which is the integer number of the lattice sides. In this case, the system can demonstrate multi-insulating phase and superfluid phase transition, and which also has a symmetry between the two coupling parameters in comparison to the well-studied model, the coupled cavity array model. And so most recently, we have also been characterizing the critical behavior with a DMRG calculation, basically by using the Latinger parameters in this model. And also, a couple of years ago, we have also shown superconducting system can be used to model electron-phonon coupling. So basically, in those two works, we studied the small polarion formation problem. So especially in the Hohenstein model and in the Shu, Schrieffer, and Heeger model. So in this case, we use transmon qubits as basically to mimic the electron spin. We started thinking about the spin degrees of freedom. So basically, there are spinless fermions in 1D. And then we use the superconducting resonators to mimic the Einstein phonons in those models with both local and non-local couplings in those two models. So this is probably the simplest many-body model that involves both bosonic degrees of freedom and fermionic degrees of freedom. And also in several other work, we also studied the circuit QED scheme for many-body system. So in particular, we studied a model, a transverse field Ising model inside a cavity. So this is a schematic diagram of the system. You can think about a bunch of superconducting flux qubits coupled to cavity, and then it can be also other type of qubits as well, for example, transmons. So what we found here is when you have a driven dissipative cavity, you can find dynamical quantum phase transitions where the system has bifurcation points and bistable regions. And at the bifurcation point, the Ising model actually going to go through ascendant phase jump between the parametric phase, paramagnetic phase, and ferromagnetic phase. And most recently, I have studied the dynamics of the phase transition at the bifurcation point, which actually can be explained with the Cable-Zurich mechanism. So this is a brief overview of several previous work. So what I'm going to tell you about now is the measurement of quantum simulators, basically the many-body correlations, and also the back action from the detector on the simulator. So we all know that if you have a quantum simulator, that's supposed to basically deal with classically hard problems, which means we don't know the answer for those problems, and also we cannot easily find the answer to those problems. So which means measurement is the only means to extract the answer that we want to find for the simulated many-body system. And then the question comes up with whether the measurement can basically accurately reflect the many-body correlations in those systems. So as I mentioned, this could look like a weird question because in traditional condensed matter systems, for example, you send a photon into your solids. You measure diffraction pattern of basically the photons, and then you basically resolve what you want to derive for the many-body correlation functions. And but then the question is why we want to ask this question. So it turned out to be like in the traditional systems, because you have large number of elements in your system, the measurement back action was not considered. So this is why you never worried about this problem. Well, if you have a practical quantum simulator, like think about if you have a superconducting system with like 20 qubits, you want to perform a quantum simulation. So back action could play a role in basically in the measurement procedure. So basically what we want to answer for the question here is whether my detector readout can basically reflect the many-body correlations in an accurate way in the presence of a finite detector back action. So before I answer this question, I want to show you an example of what would be the back action on the many-body system. So we think about a circuit QED scheme. In this case, you think about a circuit probe of quantum simulators. We all know that circuit QED can be an effective measurement of single qubit. Now think about use a circuit QED scheme to measure a many-body system. So this is a standard cavity Hamiltonian. And in this case, this is the coupling between the cavity mode and to coupling operator from the simulator that you built. This is completely a general model. So think about this just as an abstract operator for the many-body system you built. So it turned out the resonator spectrum actually reflect the correlation function of the simulator. So C omega is the resonator spectrum. It contains a term CQQ, which is basically a convolution between your correlation function of Q operator and convolved with a Lorentzian function, which basically when epsilon become very small, this is just a delta function. So this performs a measurement of the correlation of the Q operator. And let's say an example. The example is we think about a transverse field IC model coupled to the cavity. The reason we choose this model is because I can, so this model is exactly solvable, so it can give me the information of how the measurement is done. So this is basically a schematic setup. Think about you have the quantum IC model made of superconducting qubits in the cavity. So this is the standard Hamiltonian for the transverse field IC model. And the coupling operator here is basically a summation of each of the qubits in the x direction, which is the same direction as the transverse field. And so this is what you will measure from the cavity spectrum. So basically, the y-axis is the frequency of the measured spectrum. The x-axis is the parameter of the TFM. Basically, this is the transverse field. You can see that the measured spectrum is going to be able to map to the elementary excitation frequencies in the transverse field IC model. So, but there's one thing I want to mention here is in the calculation of the resonator spectrum, we use the time dependence of the operator Q, basically use the Hamiltonian H0, which is just the transverse field IC model without the coupling to the cavity. So, but the coupling to the cavity is going to generate some effect on the dynamics of the IC model. So what we did is we conducted a very simple estimation. We look at the second order perturbation approach to look at what's the correction to the Hamiltonian of the TFM from the detector. So this is the result we get. So what we found is the dominant effect on the TFM is of the order lambda squared times n. And so if you look at your magnitude of the coupling to the detector, let's say lambda n is a constant number because this is the amount of information I want to extract from the transverse field IC model. So in this case, you can find that the back action is going to be proportional to 1 over n. This means if I have a finite system, this effect can be strong, especially in the region near the quantum critical point. So this is basically a discussion of basically the back action could play an important role in affecting your quantum simulator. And so now I want to answer the question of basically whether detector readout can tell us about accurate information of the many-body correlations. So let's look at a generic system. So we have the total system with the simulator Hamiltonian HS, detector Hamiltonian HR, and the coupling HC. So this is the form of the coupling. OS is the operator for the simulator. Gamma R is the operator for the detector. So in fact, the coupling can be more general than this, but for the purpose of demonstration, we choose this simple form of the Hamiltonian. What we do is we are going to define the correlation function with the Matsubara-Green's function, basically finite temperature Green's function. So for example, for the simulator, we define the correlator. Basically, this is a time-ordered average on operator OS at different spatial and temporary positions. And you can also write this more explicitly just as an average on the density matrix e to the minus beta HT of the total Hamiltonian of the system. So basically, we consider the total system is in thermal equilibrium. So this is probably the simplest scenario you can have. And we can also talk about the correlators in the frequency domain, like CS. P is the quasi-momentum of the system, and omega n is basically the Matsubara frequency of the system. And also similarly, you can define the correlators of the detector. So the system, the relation between different correlators is demonstrated by this diagram here. So in terms of the quantum simulator, so it also coupled to a Bass mode, but what we assume in this work is we assume the only thing the Bass does is to thermalize the simulator. So there are other works in the literature that has been discussing if you have a Bass that coupled to a simulator with stronger interaction, it can have non-trivial effect, but this is not what we discuss here. So we just basically assume a simulator coupled to the Bass has a correlator CS0 without being perturbed by the detector. And due to the coupling to the detector, with the detector back action, the correlator of the simulator is going to become CS. So this is basically the perturbed simulator. And meanwhile, for the detector, so with the detector not interacting with anything, so we have the correlator, which is DR0. When the detector coupled to the Bass, we assume the Bass actually modified the detector correlator. It's become DRB. And also, due to the interaction with the simulator, the detector correlator become DR. So if you look at the system, so the detector readout is going to extract information of the simulator. So basically, what we want is we want to, from the detector correlator DR, to extract information of the simulator. So this is the whole purpose of doing the measurement. And meanwhile, we also know the simulator correlator is now perturbed by the detector. So the question is, what's measured here? Whether it's really reflect CS0 that is basically, so what the information I really want to get. So I don't want to go to detail of how to calculate the correlators under the interaction. So basically, this is a standard diagrammatic technique by treating the interaction between the detector and the simulator as a perturbation. And in the interaction picture, you can basically write down all the effect of interaction in the evolution operator here, as basically you see in this equation. And you use a diagrammatic expansion of basically the correlators. So now let's look at a very simple example. Think about a detector that is cavity and coupled to a bosonic Bass. So basically, this is my detector. Now it's just a cavity mode coupled to a standard bosonic Bass mode, and the spectral density is defined as J omega. And then you can also further assume there's a flat spectrum for the Bass, but you don't have to. And so in this case, so DR0 and DI0 are basically the bare cavity correlator and also the Bass correlators without any perturbation. So basically, this is the standard propagator for a bosonic mode, and so not perturbed by anything. So omega n is the Matsuura frequencies as we discussed before. And then with the diagrammatic technique, you can derive what the correlators of the detector is and write down the Dyson equation. So this is the Dyson equation for the detector. So now DRB is the detector correlator modified by the Bass modes. And then in this equation, you will see the self-energy term come from the interaction with the Bass modes. And if you simplify this expression, you're going to get the detector, the correlator, basically is a harmonic oscillator mode with a finite bandwidth, kappa here. And so this is for the detector mode with Bass. So now I'm going to show you two very simple examples. Basically, I have examples of two simulators coupled to the cavity detector. And the first example is you think about your simulator. It's a simple harmonic oscillator. So it's a real simple model. Basically, your detector is a cavity, so it's an oscillator mode. Your simulator is also an oscillator mode. They coupled together with this Hamiltonian. Basically, you just write down this Hamiltonian as basically the quadrature of the two harmonic oscillator modes coupled to each other. So in this case, when you write down the Dyson equation of the detector correlator, so this is the result you derived. So the detector correlator is going to be modified by this self-energy term, which depends on the initial correlator of the simulator, CS naught, which basically is not perturbed by the detector interaction. So in this case, you can show that this is my detector correlator, and CS naught, so can be expressed from this equation, can be expressed in this form. So this shows that if you can measure your detector correlation function, DRB, which is without the simulator, and DR with the simulator, you can derive your system correlator, which is the unperturbed correlator. And however, we also know that the full simulator correlator is now modified by the detector back action. So this shows that even though there is back action, the measurement result is actually not affected by the back action. So now we look at the next example. The next example is the second simulator. It's another very simple model. It's a free electron gas. Think about you can build a quantum system, can basically mimic the free electron gas. So this is the standard Hamiltonian of free electron gas with the energy and the creation and annihilation operators for the electrons. So this is the coupling between the free electron gas and the cavity mode. So this is still the coordinate quadrature of the cavity, and this is the coupling operator for the electron gas. And if you look at this operator in the real space, so it's basically just the density of electrons at position R0. So this is basically the electromagnetic field from the cavity coupled to the density of the electrons here. So then we have a number of diagrams for the system. DRB and DR are for the detectors, which is the unperturbed and perturbed correlators. And this is the free propagator of the electron. And this is the correlator of the coupling operator OS that's not perturbed by the detector. You can show that this can be written in terms of the free propagators in this form. And meanwhile, there's another diagram. This is basically a summation of the irreducible diagrams of the simulator that is perturbed by the detector, which can be shown more clearly in the diagrams here. So this is CSL, which is the irreducible diagrams. So this is the lowest order contributions to this diagram. And those guys are the reducible diagrams. So again, we can write down, okay, thank you, the Dyson equation of the system. So basically, this is a detector correlator, which also the self-energy term now actually depends on the modified correlator of the simulator, CSL. So this shows one thing is basically from the measurement of the detector, in this case, you can basically derive the modified correlator for the free electron gas, so in this form. So which means, in this case, the measurement is affected by the back action. So the question you might ask is why the measurement is affected by the back action, but in some cases not. So it actually turned out related to the nature of the coupling operator. So basically, when the coupling operator obeys the Baker theory, I don't think I have detail to discuss this. So when the coupling operator obeys the Baker theory, we can show that the Dyson equation of the detector correlator is going to depend on the unperturbed correlation function of the simulator. So like for the free electron gas, if the coupling operator actually obeys the Baker theory, so we can find that you can write down your Dyson equation with CS0 instead of CSL. So with this, I think I want to make a summary of what I just talked about. So we basically studied one question is whether the measurement of quantum simulator can give us feasible information about the many-body model that is being simulated. The conclusion we have is really depends on the property of the coupling operator. And then we found basically what's the condition this can be obeyed. So those are the preprint and recent work we have done. And finally, thank you very much for your attention.
Any questions?
Lin, if I understand you well, your detectors are switched on all the time and are coupled to all the elements of the simulator.
Yeah, exactly. So basically, we only consider one very simple situation is the detector and the simulator is coupled together and they are in thermal equilibrium. So if you look at the average we derived for the correlators, it's basically always average on the density matrix of the thermal equilibrium. So the e to the minus beta HT term.
But I could also imagine that you run a simulator and then at some stage when you think now it's there, I switch on the coupling to the detector.
Yeah.
And also necessarily I don't have to couple to all the elements. I could choose some elements that I detect.
Yeah, that
would be very different conclusions then?
Yeah, that would be different conclusions. Still, the detector back action could play an important role as well. And also there are things we didn't consider is when your detector perturb your system strongly, so whether we should consider things like non-equilibrium effect. So.
Any other questions?
Sasha.
Thank you. I just wonder, in this approach, do you take into account Hamiltonian back action, or you also take into account informational back action?
So far, we have only discussed basically just Hamiltonian interaction. We haven't talked about, for example, in fact, in the case of the detector, we talk about, say, if you look at the model we use, we have the cavity coupled to the bath mode, but which actually induces dissipation to the cavity, but we haven't talked about cases like when you have driving.
Any final question?
Yes.
It's good to look at simple, models which you can solve to gain experience. But it was now bosonic degrees of freedom and it was fermionic degrees of freedom. But our simulators, our quantum devices which we have, will have qubits. So you mentioned perhaps, you mentioned the Jordan-Wigner transformation. But let's say it's still a very limited class of problems which you can...
Sure, it's actually a very, very good question. So it's like, if you look at the strict Baker theory, right? So it's basically when you have a system, you have quasi-particle excitations, you have the annihilation and creation operators obey those basic Baker theory. However, for systems when you have like Gaussian fluctuation for the coupling operators, the Baker theory is actually approximately true. And meanwhile, as there are also discussions for spin systems, the Baker theory for spin system, there are also discussions for this back in the even 1960s. So, but we just, for demonstration purpose, we only consider those simple models. We haven't basically get a chance to talk about the other, say, for example, spin models.
Okay. Let's thank our speaker and let's move To our final speaker of the session before the break.